Okay, so we're going to go back to this problem because I didn't like how we just left that with it being so far out. So what I'm going to do is I'm going to put a times 2 here, and that means that every single line is worth 2. So if we started with -3, -3 would be right here. And then we went up 1 over 1. You can still use up 1 over 1. Like if you went up 2 over 2, it's still 1 over 1. So you can go up 1 over 1. Up 1 over 1. Up 1 over 1. So you're going to get the same effect that you would, but you wouldn't have to go as far. So your line goes out like that. And we had already decided that this was going to be, because we put a 0 in for y and a 0 in for x, and it was true, so that's why we shaded this way. And then we divided everything by 2, and we got y is less than 1/2 x plus 3. So you're going to go up 3, and then you're going to be going up 1 over 2 now. Up 1. Let's fix this a little bit. We're going up 1, which in our case is 2, and then we're going to go over 2 sections, which is 4, so it's about right here. And then you're going to go up 1 and over 2. So our graph's going to hit nicely right there. And this one is actually, I know that's a beautiful line, is actually dotted because you can see how it's not including the boundary. So when we put the 0 in and we look at it, we have 0 is less than 6, and 0 is less than 6, so this would have been going down. So our feasible region would have been right in here. And you can see it a little bit better than it being all the way off the page. Okay, so the next one here, you have a line that starts at 2 and goes up 1 over 1. Up 1 over 1, up 1 over 1. And it's a solid line. Down 1, back 1, down 1, back 1, so it'll hit about here. If I put 0, 0 in again, 0 is less than 2, that's accurate. So that's going to be true, so it's down here. Since this is true, we shade down. This one, the vertex is 3, because that makes this 0, and 1. So 3, 1, 1, 2, 3, 1, and it's not stretched or compressed, so we're just going to basically be going up 1 over 1, up 1 over 1, and it's just going to continue to go off. My dot's a little bit off here. So this one will go up 1 over 1, and so it's going to continue, but you can see how this will be dashed because we're not including the boundary. So far. Now we're going to look at this, and if we put 0, 0 in here, let's see what happens. Y is greater than 0 minus 3 plus 1. So this is 3 plus 1. And our y was 0. So is 0 greater than 3 or 4? No, it's not. So this is false. So we would only be shading inside. So you can see how our feasible region is actually going to be right here and go off. Okay. The next problem is going to be about coins. Now we did the ton problem, so it's very similar to that. They're telling you have 17 coins, pennies, nickels, and dimes in your pocket. The value of the coins is this much. There are 4 times the number of pennies as times the number of pennies as nickels. So this was that missing component of the ton problem. So let's go ahead and say that we have pennies. So this is the number of pennies. Y would be the number of nickels. And Z is the number of dimes. So the ways that we related this is the number of coins. So we said that if we took all the pennies and added the nickels and added the dimes, that we would have 17 coins. We also talked about it in money. So we said if I wanted to get 47 cents, I got that from our change. Well, we have 0.01 times X, 0.05 times Y, and 0.10 times Z. And actually, you can wipe all this out by multiplying everything by 100, and you can get rid of the decimal places. The last thing that you're going to relate is the 4 times the number of pennies as nickels. So you have way more pennies. So if you took 4 times the amount of nickels that you had, that's how many pennies that you had. And that's how they're going to relate that. So here are your 3 relationships, and they did not want you to solve. They just wanted you to define the variables and come up with the system. Okay. So on number 14 it says, explain how you would test whether this was a solution to the system. Well, in order to be a solution to the system, it'd have to be true for this and for that. So we would substitute the point into both inequalities. In order for it to be true, it to be a solution, it would need to be true for both. It would need to be true for both inequalities. So it's just asking you to explain how you would do it. You don't actually have to do it, but you need to make sure that it's clear enough on how you would do that, your procedure. Okay, number 15 is write a system of inequalities to model our situation. Okay, we want to solve by graphing and make sure that what it's saying is make sure that I know where your answer is. Okay, so you bake at least 6 loaves of bread for a bake sale. You want at least twice as many loaves of banana bread as nut bread. So the 2 things that you're talking about is you're talking about the number of banana bread and you're talking about the number of the other kind of bread, which is nut bread. So those are the 2 things that you're talking about. So your inequalities, the first thing they're talking about is you want at least 6. So you could have more than 6, but if you add these up, you could have more than 6, but you have to have at least 6. If you had 6, you'd be okay. You want at least twice as many loaves of banana as you have nut bread. So when you talk about those, you obviously have twice as many loaves of banana bread. So banana bread you have way more of. So the banana bread and the nut bread would be, you'd have to take twice as many of them to get equal to that. And it's at least that, so you're going to be equal to that. So you need at least twice as many loaves of banana bread. So you could have more than twice as many loaves of banana bread, but you don't want to have less than it. So the banana bread would be more. Okay, so now you have your equations. Now obviously the things that you also have to remember is that you're never going to have less than 0 banana bread and you're never going to have less than 0 nut bread. So we're going to go ahead and look at this as standard form. So if we were just looking at the intercepts, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. This would hit at 6 and this would hit at 6. And because it's equal to, we're going to be able to take that. 0 is not greater than 6, so our shading will go out. Okay? Then we have 2y is equal to x. So we'll divide both sides by 2 and we'll get 1/2 x like that. So this starts at 0 and it goes up 1 over 2, up 1 over 2, and so on. So this line will come through like that. Now obviously we're not going to put 0, 0 in here because 0, 0 is on the boundary. So we can put 1, 2. We can pick 1, 2 as a point. So if we put a 1 in, if we have 2 is less than or equal to 1/2, and that is not true. So we would be going down. Remembering that we still have to be greater than here. So here's our little feasible region right here. Kind of colored outside the line there, but that would be it. And you can see where our solution would be. Okay. So these are both 3 equations, 3 unknowns. We know that we would love to put our equations in the box, but we can't put them in the box until they have the same 2 variables. So we start out with one equation that has 3 variables, one that has 2 variables, and one that has 2 variables. So you can pick whichever one you want to put in here. I'm going to go ahead and pick this one. And when I put this in here, I'm going to actually put it like this. So my variables are going to be x and y in my box. So this has an x but no y. This has an x and a y but it has a z. So I need to eliminate z. So what I'm going to do is I'm going to rewrite a and c. And I'm going to have a is x plus y plus z is equal to 6. And c, I'm going to subtract the x to the other side so that I can line up the variables. I don't have any y. And then I have the z is equal to 1. So when I look at these two, and I know I don't want z, I need to eliminate the z, so I'm going to go ahead and multiply everything here by a -1. So my equation, my first equation, which was x plus y plus z is equal to 6, now I have a positive x, I still don't have any y, but I have a negative z is equal to a -1. So when I add these together, you can see how the z is going to go away. So I'll end up with 2x plus y is equal to 5. And I'm going to go ahead and bring that into my box. Alright, so I'm going to stay in this box until I have a value for x and z. So I'm going to take this guy and I'm going to multiply him by 2. If I do that, I'm going to be able to zero out or eliminate the y. So I still have x minus 2y equals 0, but now I'm going to multiply this through. So I'm going to have 4x plus 2y is equal to 10. So these are going to zero out, and we're going to have 5 of x is equal to 10. So our x will be 2. I can't leave the box though because I still don't know y. So I either choose the first one or the second one and substitute it in. I'm going to go ahead and choose the first one. So my x was 2 minus 2y is equal to 0. So I'm going to subtract 2 from both sides, and so we're going to have negative 2y is equal to negative 2, so my y would end up to be 1. Now I have an x value and a y value. Now my order is going to be x, y, and z. So my x is 2, my y is 1, and I still have to find my z. Obviously I'm not going to try this equation because it doesn't have a z. This one's nice because z is already alone, so what I'm going to do is I'm going to take the z and I'm going to put 2 in for x plus 1, and I'm going to get a 3. And there's my z value. Now, how is that different from this one? Well, this one doesn't have any that are only 2 variables. So I'm going to have to use 2 combos. I'm going to have to use a and b, a plus b, so a plus b, or a plus c, or b plus c. I need to use 2 of those and eliminate the same variable. So I'm going to investigate right now. I have to decide if it's easier to eliminate the z, the y, or the x. Since the y and the z both have at least one negative, I'm going to go ahead and pick one of them. As a matter of fact, I'm going to eliminate the y. So when I am going to eliminate the y, I'm going to pick a plus b, because you can see how if I add a and the b, the y will go away automatically. And then I'm going to pick b and c, because if I add these, all I have to do is multiply that by a 2. So I'm actually going to go 2b plus c, and then that'll be what I'm going to do. So my A is 3x plus y minus z is equal to 15. And my B is x minus y plus 3z is equal to negative 19. So when I add these, my y will be eliminated. So I'll have 4x plus 2z is equal to negative 4. So that's my first equation, and I'm going to go ahead and put it into my box. So we have 4x plus 2z is equal to negative 4. So my box is going to have an x and z in it. It's not going to have a y. So when I go to use this, I'm going to have to eliminate the y again. So 2 times b would be 2x minus 2y plus 6z is equal to negative 38. That's my 2 times b. And I'm going to add that to c, which is 2x plus 2y plus z is equal to 4. So when I add those together, you can see how we eliminated the y. And we got 4x plus 7z is equal to negative 34. And that's going to go up into the box. Kind of should make this 7 a little nicer than that. Okay, so in the box, I'm not going to leave here until I have x and z. So I'm going to multiply one of these by a negative 1, and I'm going to choose the second one. So the first one I still have. And then I multiply this by a negative because you can see how it'll zero out the x. So the x is zeroed out, and I'm going to have negative 5z is equal to a positive 30. So z is equal to negative 6. I can't leave the box though because I need the z, yes, but I also need the x. So I pick either one of these to substitute in. So I'm going to pick the first one. 4x plus 2 times my z is equal to negative 4. This is negative 12. So if I add 12 to both sides, I'm on my way to get that alone. So I'm going to end up with 4x is equal to 8. So x is equal to 2. So right now, my ordered triple, I have my x, which is 2, and I have my z, which was negative 6. I still need to find my y. So I can use A, B, or C to find y because they all have y. I'm going to go ahead and use A. So for A, we have 3 times our x, which was 2, plus y, minus my z, which is negative 6, is equal to 15. So this is 6, and this is a positive 6. So this is y plus 12 is equal to 15. So you can see that y would be 3. And that's my ordered triple. So I know it kind of has a lot of work, but if you organize it, it'll be really easy for me to see as well as for you to check your work. Okay, the last one, you're going to have 3 lines, actually 4 lines, because this is just x is greater than 0 means that you're going up here. Sorry, I just lied. I'm tired. X is greater than 0 is when you're going to go here. So that's x is greater than 0. Y is greater than 3. You're going to go 1, 2, 3. So you're here. And greater than is up. So can you see how this is the only part of that that's up? So we're going to go ahead and erase this because it's not true for the second one, and it has to be true for all, otherwise we're not going to need it. So right there's the only part that I have for solution. So we're going to go ahead and get y alone here, and you'll see that for the boundary it would be 4x plus 5. So we start at 5, 1, 2, 3, 4, 5, and we would go up 4 over 1, up 4 over 1, or down 4, 2, 3, 4, back 1. So our line would go through here. And if we put 0, 0 in there, 0 minus 5 is less than 0. Is negative 5 less than 0? And the answer is yes. So we would shade down here. But we could shade down here, but the only place so far that it's going to work is in here. Do you see how that didn't really take any spots away? This guy is going to be y is equal to negative x plus 10. Okay, so you can see how I have to be up at 10 right now. So I'm going to tell you right now, this isn't going to work for me because now I'm out of my grid. So, poor planning on my part. So what we're going to do is we're going to go ahead and make everybody just like the other one. We're going to make it as multiples of 2. So we'll start with this guy. This guy is still in here because he's 0. But the 3, this would be 2, so this would be 3. So we're going to bring that guy down to about right here. So far our area is right here. And then we have 5. So 2, 4, 5 would start right there. And then we'd go up 4, 2, 4, over 1, which is right here. So we would have this guy coming up through here. And we already put 0, 0 in there and found out that it was true, so it's going to be here so far, so we wouldn't be able to be in that back part. Then we have, this is 10. So we go 2, 4, 6, 8, 10, and then we would go down 1 over 1. Or down 2 over 2, it's the same thing. So we would go like this, which means it's going to hit at 1, 2, 3, 4, 5. This is 10. So this guy is going to come through like this, and if we put 0, 0 in, is 0 less than 10? Yes. So this is true. So this shading would go this way, which means that this guy right here is the only feasible region that we can do because we've now cut off this side. Okay, so what are our vertices? We have this one, which is 0 for the x, 3 for the y. We have this one, which was where this intercepted, where this guy intercepted, so that's 0 for the x, 5 for the y. We have where these two hit, maybe I can't see that, and we have where these two hit. Well, where these two hit, we know that the y is 3. So if we went to this one right here and the y was 3, you could see how the x would have to be 7, because 7 plus 3 is going to be your 10. Here's the only part. We need to know where y minus 5 equals 4x and y plus x equals 10. We need to know where those intersect. So what we're going to do is we're going to solve these. Now let's do this by substitution. I know I did most of the other ones the other way. So I'm going to add 5 over here. So right now I know that y is equal to 4x plus 5. That means everywhere I saw y, I can put 4x plus 5. So I'm going to put 4x plus 5 plus x, I just put this in for the y, is equal to 10. So 5x plus 5 is equal to 10. Subtract the 5. 5x is equal to 5, so my x is 1. So that means that that point is going to be 1 something. Okay, 1 something. So we put the 1 back up in here, and we get that y is equal to 4 times 1 plus 5, so my y was equal to 9. So this point is 1, 9. We know this one is 7, 3. We know this one's 0, 3. We know this one's 0, 5. So we have 1, 2, 3, 4. So we haven't written this one down. So we're going to take that and put that into our objective function. So we have 7 times 0 minus 5 times 3. Then we have 7 times 0 minus 5 times 5. Then we have 1 times 0 minus 5 times 9. And then we have 7 times, sorry, this is, I should write this up here, 7x minus 5y. So we have a boo-boo already. So this is 7 times 1 minus 5 times 9, and then 7 times 7 times 7 minus 5 times 3. So this guy is going to be 49 minus 15. So this is going to be 34. every other one is negative. So if I was looking for a maximum, this would be it. And it would have been found with 7, 3. The max of 34. Okay, so hopefully this helps you. Okay.